Hi, my name is Julius Martensen, and today I'm going to talk to you about how to recover models from data using DataDrivenDiffEq. DataDrivenDiffEq is a package in the scientific machine learning ecosystem in Julia, and hence this is also joint work with Chris Rokakis. Personally, I'm a PhD student and research assistant or researcher at the Otto von Guericke University in Magdeburg in the group of Professor Sager, and I'm also funded by the International Max Planck Research School on Complex Dynamical Systems in Magdeburg. So let us start by talking about the classical way how we tackle those identification problems. So as scientists and engineers, we are commonly, we observe some phenomena, some systems which generate data. And after a certain data collection period, we then do research, investigate the vast body of knowledge collected over the past few hundred years, and come up with a set of equations which model our problem. In this case, of course, the famous Lorentz attractor. And afterwards, after we've come up with all these equations of motion for the system and some set of parameters, we do a parameter estimation and optimize, given our model M here, for the best set of parameters which fits our data best. But as we all know, all models are wrong, but some are useful. And especially in the case of modeling, we can tackle the case of overcompleteness, right? So we have this prior knowledge about all the system, but most of it might not be needed, or most of the assumptions, for example, friction, can be modeled in various ways, how to define the best models. So what we really do is we optimize a variety of models here and pick the best based on some model selection criteria. But what if we can automate this process, and in comes DataDrivenDiffEq. So what we do is we just switch out the modeling and the optimization part, but we make the optimization a little bit harder. And to give you an overview about how DataDriven sees the overall process, is the problem itself is defined by the data. So this we will talk a little bit more in detail in a short time, but the data itself defines the problem class we are looking for. And then the model structure is defined by the algorithm. So we have two algorithms for linear or generalized linear models, embedded models in a higher dimensional space. One of which is dynamic mode decomposition, which is useful also for model order reduction. But given the brief amount of time we have today, we will not go into detail that much. And of course, sparse regression or basis pursuit. And we have a class of nonlinear algorithms by interfacing symbolic regression.jl, which is a nice package for symbolic regression, and OccamNet, which is useful for finding non-parametric but also possible non-differentiable programs or equations. And the result of our solve command is, of course, our model itself. So let's start a little bit by talking about the problem classes. The most general, without structural prior, problem class in DataDrivenDiffEq is the direct problem. So we assume that we have some sort of states, and this is the least amount of information we have here, and some output variable y, which we are able to measure. There could be also control signals which act on our system from the outside, and of course we can collect time points. Instances of the direct data-driven problem are general mappings, like for example the circle equation, where we have here x squared hidden in the u, we have y squared minus radius squared is equal to 0, or some general nonlinear mapping, or some implicit Michaelis-Menten kinetics or saturating function like here, but without the time dependency. And direct problems are applicable for general mappings, of course, but also to extract parts of unknown models. For example, in the universal differential equation paper, we use this problem class to do symbolic regression or sparse identification on the nonlinear dynamics we didn't know about. The next problem class introduces a structural prior. So instead of having just another variable here we can measure, we assume that the target variable or the response variable of our system, which we want to discover, is the next state. And of course, these are difference equations. Here is a simple linear system, but it could also be a logistic growth or something similar. And to complete our three predefined problem classes, we have also the continuous problem. And here we just switch out the target variable with the time derivatives of the state space. And of course, we have ordinary differential equations, like here, for example, the pendulum, or differential algebraic equations, or even partial differential equations. What I want to show you next is how we can use sparse identification for a simple system and a more complex system to find the missing equations of motion, and then give you an example of how to use a direct problem with an unknown friction term. So let's start. Of course, as a package of the SciML ecosystem, we solve and dispatch on the problem type, some additional arguments, and the algorithm. As I said earlier, the algorithm defines the implicit model structure. Throughout the first tutorial, we will look at the slow manifold system here, which is given by two differential equations and a slight nonlinearity in the second one. This is also used in the dynamic mode decomposition literature quite often because it holds a closed solution to the Cookman operator. If you're interested in that, I strongly recommend our documentation where this example is discussed in more detail. But for now, we just define our simulation and generate us some data and start using DataDrivenDiffEq. As a first step, we define our continuous data-driven problem directly from the ODE solution. This is useful for something some sort of model order reduction, for example. Imagine a partial differential equation in fluid dynamics where you want to do a model order reduction via dynamic mode decomposition or even SINDI. Then you can directly do that. So this is also used quite frequently to speed up simulations using operator theory. What the continuous data-driven problem here derives directly from the ODE solution is, of course, the state measurements and the time differentials. So next, for SINDI to work, we need also a basis. And the basis extends ModelingToolkit's abstract system. So what we do here is we model symbolically our states and our parameters and define a set of equations which we will use to infer the right equations of motions. Here we have two states, so we use that, and we don't have any idea how to model this except for a polynomial basis. So this gives us 10 equations of motion, or 10 possible nonlinear embeddings for our SINDI, which we can have a look at in more detail here, of course. And the basis is also used for deriving the symbolic result. So we want to use SINDI, or sparse identification of nonlinear dynamics, which was introduced by Katz and Brunton in 2016, which assumes that we can write out the equations of motion as a basis expansion in some nonlinear observables. So this, but a linear basis expansion, right? So this gives us a nice linear regression problem, but of course we want to have insight, and insight means not some Taylor series, but a sparse system. So we want the fewest possible terms inside that coefficient matrix to be non-zero. And to do that, we offer different sparse regression algorithms. The one which is the most robust is typically sequential threshold at least square, but we have also an ADMM implementation and SR3. And as I said earlier, we just solve our problem with our basis, which embeds then, or it lifts our measurements into this high dimensional nonlinear space, and solve a sparse regression problem, which defines exactly this problem. And additionally, we round our coefficients or our parameters, so the coefficient matrix here, to 1 digit. And as we can see, we come up with the right solution. Have a look at the parameters here, which also match. And have a look at the output of the sparse regression. Here we have a 3-dimensional array structure, because you can also batch your data-driven problem, which is also explained in more detail in the documentation. Then you get the best possible threshold for this, or penalty for this problem, and of course the coefficient matrix. But of course not all problems are that easy to solve, and not all can be written as an ordinary differential equation. So in robotics, it's quite typical that we have some mass matrix, which is depending on the position of the system times the acceleration is equal to sum of forces. And this can be seen as an implicit system, right? So we have a function g of or f of du dt u p t c. Again, the differential states, the parameters, time, and some control signals is equal to 0. To find this, there exist basically 2 different sparse regression algorithms. One is searching for a sparse null space, and a more recent one is SyndiPi or PI. Here in SyndiPi, we assume that some element of our lifted or our embedding nonlinear observations represented by our basis object is the left-hand side, and everything else as a linear combination can be the right-hand side. So we enumerate the search space for a good solution of that kind. In DataDriven, we again define our simulation problem in this set and include our first scientific prior, because we know we have a mechanical system, and we know that velocity is the time differential of position. So we just need to identify 2 equations here. And to come up with that, we then collect again from the simulation data, in this sense, our time derivatives, use just the last 2, and also include our control signal in the process, which is fed into here and here. So to describe the system a little bit more, we have a cardboard system here. So we have an inverted pendulum balancing on a card, which is pushed by an external force. So we have a linear movement and an angular movement. And given that we know that we have linear and angular movement, and have some slight ideas about mechanics, we can at first define our explicit equations here. So this means we also include a polynomial basis up to order 2, and then just push in some trigonometric function of the revolute joint, which represents the inverted pendulum, and also some additional equations which represent a Coriolis force, so some angular movement or some angular position times a velocity. And of course, we want to solve an implicit system, so we have to have our target variable as another variable in the basis, and include bases as candidates for our unknown left-hand side. So we do that by simply adding another set of variables here, and then add some equations. So the variable itself, something linear in the states, and something with some trigonometry, and merge that with our explicit dependence equations. And of course we have some controls, so we know it's pushing the cart, so maybe include the force directly up to a magnitude, of course, and use some additional angular measurements in the sine and cosine terms. And now we derive our basis, include all our implicit equations we defined earlier, the states, and add some implicit states. And this tells the algorithm to dispatch on CindyPy, or how to handle the variable selection. So all of the variables which include the implicit states here will be possible candidates for the left-hand side. Then we have also controls in the form of another vector and the independent variable t. Given that we don't know the perfect threshold for sparse identification, we have to iterate, or basically enumerate many different penalties. This is also done efficiently by just passing a vector here. And to analyze the result, we include some function g of x, where x is the number of non-zero coefficients, and the error, the L2 error of the certain model. And then we apply Cindy again, so solve the data-driven problem with our set of bases and the optimizer we just defined. And here an enumeration over all possible candidates for the left-hand side is performed, and it finds the optimal right-hand side for that. And here we see again the problem definition with the plot recipe, so our states, our differential states, and our input signal, the estimation of the output of our sparse identification model, and the error overall. And we can also have a look at the inferred equations of motion for the acceleration, and we see, okay, they matched. So here we have our torque, which is acting on the pendulum, and we have our linear force, we have our Coriolis terms, and we have the denominator of both equations. So this concludes the linear part. As I said earlier, there's also the dynamic mode decomposition, which is useful for model order reduction and different stuff. And now we want to have a look at the nonlinear discovery, and we will focus on, as I said again earlier, symbolic regression.jl. So what we want to do here is to be ready for the script, which I've run in advance, given that symbolic regression relies on a population-based estimation. So we typically need a higher or a certain amount of time to find a right solution, because it's adapting slightly the equations it finds and evaluates over a bunch of population members to find the right equations for motion, or equations of the unknown regression problem. So what we're interested in this example here, and let me just show you the plot, is a nonlinear pendulum. And especially we want to identify this friction term, which is nonlinear and not something encountered typically, but nonetheless valid. So we have a cosine of the angular position and some possibly scaled, in this case 1, input of the control torque acting on the pendulum. We again simulate, then we use the array of the simulation with some noise attached to it to define our problem, include the control signal now scaled and as a function of the states, the parameters, and time. And in this case, we directly compute the target of the regression of the direct data-driven problem. But otherwise, as I said, or you could also use the UDE framework or some other surrogate model which is able to learn an arbitrary function inside a differential equation. So we define our direct data-driven problem with the states, our target variables, which is also an array. So also always a matrix, never a vector. The vector is always given in the time domain here, and the function u. And then we plot our problem, which we can see here. So for a direct data-driven problem, we see the input variables or the independent variables and the dependent variable and some control signal. And to call on symbolic regression, we have a wrapper struct, which includes to define unary and binary functions. So in this case, we will use addition, multiplication, subtraction, and a cosine function. And as loss, we use the L1 distance loss. So as I said, we use an L1 distance loss and wrap everything in our equation search struct, which again dispatches, given the problem data and the algorithm and some additional keywords. And we pre-computed this solution here, and again it gets transformed into a data-driven solution. And as I told you, we typically need a large search space for this. So what we see here is that we don't recover the ground truth, and this is also due to the time, of course. But what we see is that our error is quite good. So even if we didn't have or were able to recover the full equations, we have a model which models the data really, really good. And just to give you some perspective, I will run it again, this time using a higher iteration count. And stop the recording for a moment. So we can see now that after 1,000 iterations or 15,000 iterations, 11 minutes, this is running on an M1 MacBook. We derived at a new solution, which is slightly better, but again, similar to what we already saw here. And this has several reasons, one of which is of course the data availability, then the population size can be varied. So what I want you to take from this example is, even though we match quite good here from our error model and the overall performance, the solution is not the ground truth. And this has, of course, reasons. For example, nested cosines and stuff like that don't make sense really in this context, because we have just a pendulum, and nested cosine and sine functions most likely make no sense in this context. But the overall model can, of course, be tuned with hyperparameters. Nevertheless, we have something which we can work with from the data. So let's jump to a conclusion. What is DataDrivenDiffEq? It's a collection of algorithms for data-driven system estimation and structural identification. It's strongly integrated with the SciML ecosystem and the symbolics ecosystem, relying heavily on ModelingToolkit and symbolic utils, of course, for our system definition and how to define our priors here. So we also saw it defines a common API for model discovery, model order reduction, and symbolic regression. If you have any, or if you want to go further and know more about data-driven, we have slightly good, maybe better documentation up, with different examples, of course. So if you go to the GitHub repo and have a look at the stable, we have various examples on how to use different methods, also the Koopman operator and its interconnection with sparse identification, how to use batching, also symbolic regression here. And pull requests are always welcome, and of course feel free to write me an email or a DM on the Slack. And in the future we will most likely restructure the package a bit and divide it up into several sub-packages similar to optimization.jl, and also provide more algorithms. For example, deep symbolic regression, which uses recurrent neural networks to learn the equation tree, the underlying expression tree. Yeah, thanks for your time and have a great JuliaCon.